Since the completion of the formalization of the Clay-Thompson theorem a couple of years ago, his name has been practically synonymous with big proof. So any introduction just seems kind of redundant. So instead, let me just add some personal observations. I had a wonderful opportunity and the good fortune to be able to participate in the project on a sabbatical year in Paris in 2009 to 2010. And soon after arriving, I realized, very quickly that George and I had very sort of different attitudes and thoughts about formalizing mathematics. I mean, from my point of view, mathematics has been going on for a couple of millennia, at least. And my thought was that there are very good reasons why mathematics is done the way it's done, the way it's presented, the way it is. And so my thought is that the goal of interactive theorem proving is to the ideal is, as much as possible, to formalize mathematics the way it appears in the textbooks, the way a mathematician, would be inclined to write a proof. George's attitude, it seems, was rather that, well, now in the last few decades, we've learned from computer science a lot about how to build large, complex systems and libraries and so on. And so George seemed to take it that, the challenge of interactive theorem proving is to understand how to transfer some of those insights back to mathematics. And now I've come to believe that the truth is really somewhere in the middle. I mean, it's certainly the case that computer science has learned a lot from mathematics about how to develop useful abstractions and how to develop complex bodies of knowledge and in modular, encapsulate information and develop knowledge in modular ways. But I think it's equally true that now mathematics has important things to learn from computer science in that regard. And so George's insights are always, I think, very valuable and important in that respect. And so I'm looking forward to hearing what he has to say on that.
Thank you. Well, actually, I agree completely with what you say, and it's an extremely nice introduction to my talk. So the talk is about the MathComp library, and as you pointed out, this is joint work with many people. I've listed 14 below my name, 5 of which are in this room, including Jeremy. So I couldn't have done it without them. And the talk is about the library, and I'll try to explain, in some sense, that my design goal in sort of building this was to try to make it as unremarkable as possible, so that you could, whenever possible and relevant, you could do math the way mathematicians do, but not to the point of painting yourself in a corner and putting yourself in an impossible position, because mathematicians have this way of escaping saying, this is obvious, or it's clear that, which you don't quite have if you actually want to have a fully formal proof. So in this talk, I'll show some of the normal stuff, but mostly what you'll see are the quirks and the places where things got invented. So I guess I should first start by explaining the title about frames and scaffold. So if you're building a house, well, in order to have a good house, you need to have timbers that hold the thing up. And this is roughly how one tends to think about, at a first glance, or a first approximation of formalization libraries. They're the big pieces that hold up the nice constructions you're going to build to solve more interesting problems. So they're kind of less interesting than fancy trimmings on the house, but they're big, solid, chunky, and standard. In some ways, they're not so interesting, except they actually have to fit together, and that's perhaps the part that is actually harder to achieve when you're building a formal computer compatible library. But apart from the framework, if you want to put up a house, you usually need some scaffolding. So this is still framing, but it's sort of temporary framing that you intend to throw away. And much of the talk is going to be not as much as about the framing, because that's fairly standard, but about the scaffolding, because that's the part that tends to be neglected, because in some ways it's intended to be thrown away, and people that develop library are kind of a bit reluctant to put in stuff that ultimately disappears when people use their work. And I should probably add a third item down there, which are also things that don't actually stay in the house when, but are useful to putting it up, which are tools. And I've worked on a number of tools that help develop a library. They're basically captured by under the generic name of the assessreflect extension to Coq. And I'm not going to talk much about that. The difference between tools and scaffolding is that you need to become proficient in tools. So tools are very nice. There's a long tradition of working on tools. But if you do everything by tools, then you end up with lots of specialized tools. And then this is not so great for people that actually want to use your library, because they have to learn to use all these specialized tools. Whereas scaffolding is just a bit of theory that just looks like normal theory, but that you just intend to throw away.
Tell that to the next builder I meet. Scaffolding is just a bit of theory.
So that's my slide about the framework. Just to give you a short table of contents of what's in the library, and in some sense, not much in that you'll have a much more impressive list of things in the next talk. For example, one thing is that deliberately it's avoiding anything that has to do seriously with analysis. So not even basic calculus. And it's only a very small fragment of the nice map that Ursula showed yesterday. So you've got sort of up there are the really ground basics, just straightforward arithmetic, finite combinatorial objects, containers, lists, sets, functions, and so on. And perhaps not so standard, very standard in math, but not so standard in formal theory libraries. A reasonable amount of stuff on elementary number theory and the big operators, which I'm particularly proud of. And I'll talk about a bit more about them later on. Then the core of the library, and probably I guess the most useful part is still the top part. So the people that use the library, the reason they're going to want to use the library is this top part. And of course that's part to do with the fact that people that develop formal proofs tend to develop them in combinatorics, and this is probably the only part they're seeing, or logic. So the second part is also the second most useful part, and it's just very basic undergraduate algebra, but still going on to Galois theory. There's probably so you've got the sort of basic setup of algebraic structures and but also interesting algebraic objects that work well together. So you have polynomials and matrices, but you can combine them to have polynomials of matrices, matrices of polynomials, and you've got the relevant theorems that are pertinent to these combinations, like the Cayley-Hamilton theorem, which has a 3-line proof. And there's a fair bit more, a somewhat larger collection of group theory, which goes on to the next topic, which is graduate group theory. The reason being, of course, that the whole library was developed to support the proof of the outer theorem, and therefore we have a bit of the Mexican hat effect that the library is a lot more developed under the theorem we were looking at. And so that goes into more specialized topics like modular representation. I've got a horrible typo on Frobenius groups. So Frobenius groups, special groups, for more exotic properties of solvable groups, and apologies to real mathematicians out there that might think that some of these topics belong to undergraduate. That was just my assessment of which ones I found sort of easy to follow and which ones require significant investment on my part. And all the way down to the more exotic bits of using the proof of the Phi-Thompson theorem. And then there's another bit that's a bit on the side, and that has to do with constructive math. So largely, I guess there's a fair bit of stuff, a small amount of stuff that's related to constructive math in the library itself, but its main aim is to just shove the constructivity under the carpet so that you can do normal plain mathematical reasoning, even though we're working in a core logic that's constructive, and we don't use the axiom of choice. So it's the axiom of excluded middle. But that's sort of a minor part of the library. It was part of an exercise of showing that, okay, you can actually do constructive math and not feel it that much. But there are a few places where it ends up being a tight corner. And so there are a few more specialized parts developed mostly by Cyril and Assia on quantifier elimination. And then a bit about the construction, the constructive construction of the algebraic numbers, which is not as obvious as one might think. It basically requires to do a constructive proof of the fundamental theorem of algebra. And the development has a this nice quirk that it actually has a constructive version of the Artin proof as opposed to a completely exotic and elementary proof. Plus the traditional is actually just taking the normal math proof and rearrange it so that it fits constructivity. So here's a picture of the library, which sort of gives relative size. I must apologize that this is what you can find on the website. The website has now much fancier and reorganizable display, but because it's user rearrangeable, its defaults are not quite as good, and so it's hard to pick out a version of the display that actually fits nicely on the slide. So I've resorted to the older one. What's interesting, I guess, is that only the very bottom, this is the combinatorial part of the library, and that's the only part that's used to prove the four-color theorem. And the top part, the lofty tower up there, is the Phi-Thompson theorem. So that's all the specialized, the very specialized material. And sort of everything in the middle is your basic, I guess, basic algebra is here, and then more advanced group theory is up there into two parts, where the part over here is the solvable part, and the part up there is the character, below is the character theory. And I guess it's sort of important to see to understand when you look at a picture like this, because anyone can come up with a picture that looks arbitrarily complicated or arbitrarily simple. So you've got to get a feel for the scale of the thing and figure out how big are each of the blobs. And again, in computer science, there's a big debate on how large you should make modules, and the same thing occurs for proofs. So some people want to have just one concept, almost one lemma per unit, and on the other hand, you might want to have just one blob that covers an entire topic like algebra. And this is sort of in the middle, where each blob covers I guess a month's worth of a syllabus. So so this is the blob that has for example, that has basic definitions about finite groups and things about group morphisms and automorphisms and quotients are in separate blobs. And the main contents of each blob is summarized in a blurb at the top of the file. So the top of the group file has a lot of constructions because it's introducing a new concept. So there's lots of notation to go through. And later on in the file, you get lots of little theorems. So in some sense, this is the part of the file that would correspond in a normal textbook to just stating the Lagrange theorem, which would be I guess almost the top theorem. There are a few variants, more general variants listed up there because they're they happen to be proved first, and then there are various consequences or equivalent formulations, and this is sort of the scaffolding part, really. In a normal text, you'd probably see just the Lagrange theorem, and then you'd be expected to do the swizzling around to use whatever consequence of the Lagrange theorem you actually needed in a proof. It's actually much easier if you want to build a formal proof to be able to say precisely what you want. So you get a number of variants of this. I guess another bit of scaffolding that's also visible in this is the naming convention for lemmas. Now, this is a place where I guess traditional mathematicians are notoriously bad at figuring out names. In fact, I quite remember Jeremy complaining to me that I insisted that everything should have a proper name that's both manageably short and indicative of what the thing meant. And he complained that this was really hard to do. And this is, of course, one of the basic skills you acquire when you started developing software. So in particular, this shows off the system of suffixes that are used to avoid having very long names, because mathematicians like to give long names to important property like associativity, commutativity. Since these are things that are actually very elementary and which you use all the time, if they had long names, then you couldn't really use them practically, or quite as practically. So there's a system of abbreviation that's reasonably consistent, so again, one of the things that disappears completely once you actually use this, but that's really useful in making it more practical. And I guess that was a summary. The real detail has all the proofs, and probably the main message in this file is that, as most basic libraries, all of the proofs are really, really simple. In some sense, most of the content of the library is what you saw in the previous picture on that slide. It's picking out the right set of variants. That's hard. Proving stuff, even proving the main Lagrange theorem, is just a couple of lines, as it would be in a basic textbooks. And that's sort of the general rule I've found in developing libraries, is that you have this sort of Pareto law or power law, which means that almost all of your theorems have very short proofs, except you've got the one few hard things, like I don't know, the fundamental theorem of calculus or the fundamental theorem of algebra, that have long proofs. And then those proofs are so long that actually most of your proof lines when you're developing a library are in those theorems. So part of the standard contents is providing the basic framework for doing algebra, so the hierarchy of structures. And the remarkable thing about this is that it's utterly unremarkable. And in fact, it's so unremarkable that there's a single file that contains all of these, because there's just no significant theory to be developed, so it can all be stuffed in one file. And even that file covers things that are very often covered from elementary presentation of rings, like Frobenius automorphisms, or the categorical structure of algebra, the properties of morphisms, or the topos property, the various forms of algebraic subsets. And those are really important to when working, especially in character theory, because you've got all sorts of subsets that are weirdly closed under some operations but not others, like monic polynomials, class functions that are characters, which we'll see in a bit, or algebraic integers, or natural numbers, the natural numbers subset of algebraic of algebraic numbers. And these combine in an interesting way to let you. So if you look at something like matrices, well, they're going to rely on many things, so they can have a very small definition, but which calls upon lots of sub interfaces, including the big operators we'll see in a minute that let you write these nice definitions. So that's the library, and that the one thing that should have been that you might note in that matrix example is that it does rely the fact that matrices mesh so well with the library relies on the fact that there's a lot of intention that's coded in the library. So in traditional math, you don't really state the intended use of a theorem when you define it. Notation is very concise, because that's the way you can efficiently communicate information on a blackboard, whether on a blackboard or in a paper. But as a result, it's overloaded, ambiguous, and the patterns that are used to organize proof arguments usually aren't covered in textbooks. There's sort of things you're supposed to learn organically by doing lots and lots and lots of exercises. And that's where the scaffolding comes in. That's the part where we try to capture all of these things inside the formal library, so that everything works smoothly. So part of this, so the part about stating the intended use, that's actually done by changing the framework. So this is the place where I decide to sort of do something that's beyond normal math, and in this case it's exploiting the type theory. And all formal systems, even the ones like Mizar that are based logically on set theory, actually have a type theory on top of them, so that they can do this. Otherwise it's impossible to do any realistic math. Now perhaps one word of caution: it's easy to overuse type theory. So one of my early sobering experiences was when trying to work out the math needed to prove the four-color theorem, which is very elementary math about elementary graph theory. So about the only concept I had to use was paths. And I think it took me 7 iterations to actually understand how to do it properly. Because I just started, my first attempt was to do it by the type theory book, using a very general inductive relation to describe the path objects. So it's basically a trail. A path is a trail of points that satisfy a certain successor relation. And if you try to write it as a dependent family, then really it's interpreted as a path in the hot sense, meaning it's really a form of equality. It's just saying, okay, any path object is either a nil or a const, and when you try to use the property, it's going to replace your path with a brand new nil and a brand new const, even though you might know other things about the path. And it makes reasoning extremely complicated, because you're constantly fighting the cock, which is trying to do something which you don't want it to do. The second attempt was to say, okay, I don't really want to use identity types here. I just want to have this succession property. So let me just use a simple dependent type where I just embed the succession property inside the list. And so the downside of this is that every time you want to define an operation on paths, you have to basically do it from scratch. So even though you've got a reasonable theory of lists, you can't use it there. You just have to reinvent, to just redo everything. The real problem I realized was that as I moved along the proof, I realized that I needed to have several relations built on the same set of points. So I had several graphs that were layered on. This is the sort of basic combinatorial model I use to represent combinatorial maps. And so I want to use the same trails and say that they're paths for different relations. And it's impossible to do it this way. So the way of doing it is sort of going back and forgetting about all of the theory, and just use make the trail explicit, use a predicate, and then you can just use the straightforward list operations. And now you have it's much easier to use. You have easy rewrite rules to handle the combination of the predicate and the path logic. And because of the elaboration process in Cog, the implicit argument filling, actually you just pass the predicate, the evidence that a certain trail satisfies the path predicate as a representation of the path object, because in the dependencies of the type, you'll find all of the information you need. So what's the start point, what's the relation is involved, what's the start point, and what the trail is. Just passing the proof contains ultimately all of that, all the things that the proof is talking about.
What was the little t? After the fixed point, it says if.
That's a typo. It should be a p. Another example of this occurred very early in the formalization of group theory. The realization that if you just try to map straightforwardly or naively group the set theoretic presentation of group theory into type theory, saying, okay, I'm going to use, I'm in type theory, so I have to use types to represent groups because, well, I have a hammer, so everything looks like a nail. Well, you end up having to define all of these notions. And then you also have group sets that work pointwise. But then you realize that actually this is the wrong way of working, because what you're doing all the time when you're working in group theory in general, and especially finite group theory, is having the same elements that belongs to multiple groups. And this is the one thing that type theory doesn't want you to have. You don't want to have the same objects have multiple types, because the types capture the intended use of the object, and so having multiple intended uses is bound to introduce confusion. So it means that you shouldn't. We should go back and reconsider the fact that really group theory is a misnomer. It should really be called subgroup theory. We're always working with subgroups. And so the big insight was realizing that, okay, well, so the groups are actually mathematical objects. They're not mathematical objects, which are the way you use types when you do a formal development. There's sort of categories that help you classify assign properties to mathematical objects. Groups are proper objects which you're manipulating all the time. And so the proper objects are going to be sets, and it happens, and you can certainly represent set inside type theory using essentially predicates. You can do something slightly better with respect to extensionality if you have finite sets, which is what we're doing in this library. Now we can separate, now that we've decided that groups are their own things and they're sets, we can decide to look at the the type properties, and the type properties should go with the type. And so what are the type properties? It's the binary operation, right? The point of having x that's both in G and H is that the multiplication in H and the multiplication in G are the one and the same operation. So you have the part of the group information that's attached to the type, and part of it, the actual extent of the group, that's contained in the data, and the extent has to satisfy the usual closure property. And when you're manipulating a group, you want to actually have a subtype of sets. So you want to use a group as a set, but that has this property. And so there's the question in type theory of whether you want to specify the subtype of set as a type, or as or just have the property hang on the side. And it turns out you can actually use the elaboration in Coq to infer the property, the closure property behind the scenes. And so you can sort of cop out and for the most part, consider that groups are sets, and somehow magically the proof system will figure out. So that's how traditional group theory would normally look like. And now that we've decided that groups are really subgroups, it just got a little simpler. So now we.
Can you do
So subgroup becomes just plain group, and you don't need. And when you are talking about a normalizer, you don't have to give necessarily give an enclosing group, because if you're because you always have one that's implied by the whole type that you're working in. And indeed, if you look at group theory textbooks, they will often, although they will formally say, oh, the normalizer always needs to have a bound, they will often, in the actual development, drop the bound, saying, oh, well, let's be done with this. We don't really need to talk about this all the time. And here, you actually have in the formalization something that says precisely why, when you don't want to talk about the bound.
Presumably on the third line, those are just inclusions, they're not subset.
Yeah, they're just inclusions. And in fact, the concept of a group set gets merged into the concept. Can be merged into the concept of the group type, because you can have you don't need to have the cancellation property necessarily attached to the product and inverse, and generally monoidal structure over the product and inverse. So if you separate the two, then you can actually embed the concept of a group set inside the concept of the group, which is really nice, because then you get to overload multiplication. And this has interesting consequences for the all-important concept of a group quotient. So here's the formalization of group quotients, and I'm not going to explain the detail of this, except that it's actually a generalization of what you traditionally write in group theory. So in group theory, you're only allowed to write G/H if H is a normal subgroup of G. So it's a partial definition. And it's really hard to handle partial definitions in a formal logical system, because technically they're supposed to prevent you from writing stuff. Except mathematicians play it very fast and loose with those interdictions. They'll often write something at a point where it's in principle forbidden, then explain 5 pages later that actually it was quite reasonable to write it this way, because there was some convoluted reasons for which you could do so. So in the case of group quotients, there's a good reason for having that prescription. It's the same reason for not allowing division by 0, which is that it lets you apply cancellation just by pattern matching, and it's always tempting to do cancellations, and so that you would not be tempted to do illegal cancellations, you're prevented from even using the notation should you be in a situation where you wouldn't be able to cancel by just looking at the symbols. And in this case, because we have a formal theorem prover, we have a safety net. The Coq is not going to let us do a cancellation where when you don't have the proper inclusions or normalization properties, which are, by the way, weaker than the traditional normal subgroup conditions that are imposed. And furthermore, if you look at group theory textbooks, they're peppered. So we use an extended, and it's actually quite easy to extend this notation consistently to have to work for arbitrary subsets. And so that right-hand side might look a lot fairly complicated, but it actually occurs multiple times in any group theory textbook. So because they've got the wrong notation convention, because it's trying to solve, or rather it's the right notation convention if you want to solve this cancellation problem, but because it's a problem I don't have in Coq, I don't need that restriction rule. I can generalize the notation. And surprisingly, most of the theory generalizes to this notation, so that there are very few theorems that require you to actually prove normality in order to be able to use them. And I should probably move on from group characters in order to talk about other subjects. So one of my favorite pet peeves is notation, and I'm actually quite proud of what eventually got achieved with this formal group theory library. That I could take a half page like this one from the Veit-Thomson proof and write it in Coq in a way that pretty much preserves up to using ASCII art, because at the time Unicode support wasn't all that good. It was something that looks really like the original text, and that was quite. That slide always seems to be quite popular with people that actually do group theory for a living. That they see, oh yeah, actually, this formal stuff looks like what the maths I know and love. Perhaps I might want to look a little more into what I can do. Then, of course, they see how we do proofs, and they decide they have better use for the time. But so a lot of this is just down to overloading and putting the right interpretations. Well, we've seen a number of overloading in a number of talks, so I'm going to go quickly over this just to point out that there are actually two kinds of overloading that are practiced in traditional programming. There's parametric or uniform overloading, where your symbols always mean the same thing, but their meaning is to actually take their meaning from an additional parameter. And there's ad hoc overloading, which is just to say, well, based on the immediate physical context, decide what meaning you want to assign to each symbol. So this is based on physical location, and the other one is based on logical connections. So parametric overloading is what happens if you declare parameters that are in a element of a generic group type. So here's the typical group type structure, which would have a carrier type, so represent the type to which the elements belong, and then the operations and properties of the operations, whatnot. And so if you declare a universe like this, then you can declare constants whose type is given by the type component of the structure. And then generic product can be interpreted by filling in the missing parameter information as to which structure to use to interpret the product. And this can be done by just straightforward process of unification. So this is the straightforward elaboration process that occurs in every functional language. Now, the interesting thing is to make this work for ad hoc cases. So, like if you had a specific construction, like you have elements that are manifestly in a quotient group. So they're cosets, and you're multiplying two cosets together. So, so how do you interpret this? And And this, the mechanism I'm using for resolving overloading is a little different from the one you've seen over the past couple of talks, which is based on type classes, where you would just have a hanging parameter here that describes, so you wouldn't, the type parameter wouldn't be contained in the structure. So you would just unify the types normally and decide, okay, this is a product using some interpretation of multiplication over cosets. And the so this is and the type class mechanism that was pioneered in Haskell is a way of doing this, and there's a version of it in Coq and Isabelle and Lean, but this is not quite what I'm using, though it'll amount to the same thing, because here I've bundled the structure all together. There's a single object that represents a group, or an enclosing group. And as a result of this, when Coq tries to do elaboration and type inference, it gets a unification conflict. So it has on one side, on the one hand, the star tells it that the argument should have type G sort of some structure. On the other hand, type inference from the expression tells it it's a coset. So there's a way out of this. If we were in Hall or in any first-order logic-based system, this would be just a straightforward error, because you've got different symbols. There's no way these things can be identified. But in Coq and Lean, the logic is truly higher order in that the syntax itself has meaning, and you can compute expressions. And so this really means take a structure and extract this G sort here. It's not a hidden, it's not a symbol that has a purely abstract symbol. It's something that says, get out the type component. And so if you tell Coq that, yes, there's a canonical group type for cosets, then it can use it to plug it in this case, compute, and then check that the equation works out. And so that's the mechanism I'm using. And the reason for using this mechanism is that it's about equivalent in expressive power to type classes, but it's better behaved because the inference doesn't happen after the fact asynchronously when the theorem prover feels like it. It happens exactly, it's driven by conflict. So it happens exactly at the point. If there's no conflict, then the constraint gets propagated. And if eventually we have to figure out a certain group type, we do it at the point where we have the right-hand side that's been, that forces us into a conflict. So it's better behaved, and also because it's tied to unification, it works well with other operations you do in proofs, which is to look for patterns. So you can use these classes not only to resolve overloading, but to tell the prover to look for certain patterns. And I'm going to skip all of this because you've seen. So one of the ways it's used is to implement generic lemmas over big operators. So big operators, which a lot of slides I just skipped all over, but I'll include them in the PDF. They're just what you write with \big in LaTeX. So sums, products, GCDs, central products, whatnot. And there's a generic theory of them, which is very nice because you have lots of them, and if you don't want to redo, there are sort of 80 lemmas in that generic theory, and so you'd rather not have 10 times 80 lemmas if you have 10 versions of big operators. And the reason you can have the generic lemmas is that you can use the structures to give properties not just of types, but also of actual mathematical objects. So types are kind of meta objects, but you can also use these structures to give properties to objects, in this case to the operation that's being iterated. And that means that this rule, for example, that, let me see if I can point here, this rule that splits off an operation when it's commutative and associative, it can actually be read both ways because, so it only works for an associative commutative operation. But we can use the structure, the unification, to recognize in an expression where you have operators that are commutative and associative, and where you might look for this, and so you might know, you would know where to look for this pattern. And here's a more interesting, another interesting example of this. So there's similarly a class to interpret which functions are linear. And the notion of linearity that's supported is actually quite general, because as it turns out in character theory you have lots of sesquilinear functions because you've got a Hermitian product on characters. They're functions over, that are complex valued. So you've got this notion of having a multiplication and combining it with a morphism. Plus, the notion of multiplication actually changes. You, if you formalize module theory, you have to distinguish between scalar multiplication and the internal multiplication in modules or F-algebras. And if you have scalar linearity, you want to translate this, which is module multiplication, to scalar multiplication. If it's module linearity, vector space linearity, you want to keep the scalar multiplication. And so it's actually possible to build an interface that handles both cases elegantly. And it's even possible to use additional structures to recognize the right-hand side of this equation so that you can rewrite, you can use the same equation to push a linear function over a scalar multiplication, or to recognize when you have this combined scalar morphism application multiplication and go the other way around. I'm going to skip over group presentations, which is another more extreme example of notation where you are reinterpreting the syntax completely. And just talk about direct sums, which are another example of doing this. In this case, you're interpreting a formal sum of vector spaces as, or a formal sum of matrix row spaces as a not just representing the result, the resulting space, but also the individual terms, so that you can have a predicate that says, oh well, this sum is direct, and this is a predicate that's actually non-extensional. Its meaning depends on how you've written the expression. And you can actually do that in a talk, and it's very useful to develop proofs in concerning eigenspaces and eigenvalues, because eigenspaces tend to be direct sums. And so with a little bit more of scaffolding, in this case in the form of a predicate that handles conditional inequalities for integers. So the interesting thing of the property of the rank sum is that it sort of has this convexity property that the rank of a certain sum is always less than the sum of the ranks, and when you won't have equality exactly when you have a direct sum. Of course, a direct sum is a very strong combinatorial property because it gives you uniqueness of decomposition. And so a typical form of reasoning you find a lot in character theory, which is about norm inequalities, is to have circular chains of inequalities, and you just sometimes along the way you get these rank inequalities or other convex inequalities like the Cauchy-Schwarz or arithmetic geometric mean inequality. And so you get these chains, and you at one point and when you somehow end up back where you started, then you say, oh, it's a cycle, so everything has to be equal. Therefore, all of these conditions have to hold. And so having just a little bit of scaffolding, which is having a placeholder for this predicate condition, here we have the direct condition, makes it possible to capture this sort of reasoning, which would otherwise require you to repeat basically the chain of inequalities twice in order to make your point. So here's an example of it being used in a real proof somewhere in I think the second section of the first half of the Phi-Thompson proof. And so here's the rank lemma. So essentially, after you've processed all of these top lines, you've got all of the various conditional inequalities, and then you just use the transitivity lemma to chain them together, which gives you one huge inequality with a condition that's a conjunction of things. And then you prove that this is an equality, and you get that all the conditions are true. And then you just break up the and to get a bunch of facts to prove an interesting theorem. Okay, I had one last bit about sort of the ultimate piece of scaffolding is when you just add a bespoke meta reasoning inside your system. So there's a very nice example of this in the Phi-Thompson proof, where you've got this integer norm problem of inferring integral vectors from dot products condition over a matrix. And if you just naively encode the problem to SMT, then even though it's a relatively small problem, it's this 2x4 array you have to work with, it's just not in the sweet spot of the SMT and not in the sweet spot of the heuristic, and so the whole thing blows up. Since those are vectors that actually have coordinates at most 1 or minus 0, 1 or minus 1, you can actually encode this in SAT, but again, if you do a naive encoding and you don't use one of the fancier SAT solvers, this fails miserably. And you can, of course, because it's a small problem, if you take a nice compact encoding, then the SAT solver will find the solution just by pure brute force. But then, actually, the effort required to justify the encoding is bigger than the effort required for just modeling the vectors straightforwardly in the logic, writing a few model checking, 3-line model checking bits of code in Coq, which then let you translate this big combinatorial proof into a shorter combinatorial proof that just uses a bespoke logic. So it just uses uses a formal quoted representation of the problems, and then it just uses the decision procedure or other code transformation procedure whenever it has to swizzle things around in a specific way. So you get a formal proof that's actually nicer than the original. And it's so much nicer than just doing the formal proof makes you realize that about a third of the original proof is just unnecessary because it's a symmetric case, and the symmetry was just obscured to the author of the book because, well, this formalism got in the way. And I've got an even better example of this in the proof of the four-color theorem, where there's this bespoke language for solving the combinatorial problem of whether your decomposition is complete. Okay, so that was it.
Before I take questions, there's just something I noticed. So in the United States, and I take it all over the world, kids are really obsessive about these fidget spinners.
Yes, I know.
I just noticed that maybe
we predate fidget spinners by a few years.
Mario.
The question mark if C1 in your example about circular inequality, what type is that and how is it defined?
So it basically means A is less than or equal to B, and they're equal if and only if condition C holds. So it's just a definition for that. It's roughly a pair of Boolean equalities. But just a little bit of it's just this tiny bit of scaffolding that makes an entire lines of reasoning possible, and that for a very modest investment in the arithmetic basic arithmetic file, yields huge gains in writing down complicated proofs at the time. So it helps you at the time where you need it most, when you're doing something really complicated and really don't want to be facing additional complexity from your formalism at that exact place.
Arnold, and then Frank.
You had a slide, textbook to digital formal text.
Yes.
Was that done automatically or semi-automatically, or was it done by hand?
It was done by hand, but and there's some bit of interpretation in it. But you could you could certainly get bits of automation to do this mostly automatically. Of course, the reason it was done by hand was that that paragraph pales in comparison to the 6 or so pages of proof that follow.
It would be interesting to have the converse, because while following your talk, I understood almost everything you said, but almost nothing on what was on the slides, because it was written in a form that is completely unintelligible to a mathematician.
I think most mathematicians can read LaTeX in the ASCII. So if you're not
Some training also.
so this is designed to be sort of on the LaTeX level of, but I agree that display, there's been improvements in display, and well, you'll see in the Tobias' talk that Isabel has nice display features that let it process statements through LaTeX and give them more traditional printouts. Obviously, if you're actually working with the statements, you actually want to have the formal form that has the full details in it, because there are little bits of the ASCII syntax that are actually necessary to remove some of the ambiguities that the elaboration process in Coq can't quite handle.
Rick?
So I'm very much impressed by all this. So this is E0. That Tribulets always said, like, experience not only doctrine. I mean, you only get a library as good as this by actually doing all this mathematics, I think. But I wonder how much of this is dependent on the idiosyncrasies of Coq. So you have this Coq machine, and you have all kinds of features everywhere, and then you use all those features because it allows you to do this wonderful stuff.
So I don't quite use all of the features of Coq. There's some like the actual type classes, which I tried to use, but didn't turn out so well. There's lots of idiosyncrasies, like the exact details of how, for example, that generic rewrite rule for generic linearity works. And I'm not particularly proud. Well, I am, but for the wrong reasons. Of the hacks that are needed to get this to get Coq to do this. They're more a case in point of showing that yes, actually there are cool things that can be done, and it's desirable to have those things. I would wish they were more straightforward to do, and the I guess case in point is probably the way hierarchies are encoded using the unification mechanism I showed, which requires quite a fair bit of boilerplate to be written down in those generic structure presentation files. And these could be certainly automated. It's just Coq doesn't handle it, and I wish it did.
My question, please, you didn't allow me to. So what would be the main features to be added to Lean to be able to port this kind of approach to Lean? That's the actual question.
Lean has all of the essential features because Leo is an excellent listener.
Next question.
Though I'm not quite sure the unification hints are, well, they would need a whole more packaging to do this better. But since Lean is now meta-programmable, I'm pretty sure I could figure out a way of doing it.
Vladimir, did you have a question?
Well, I had just do you use implicability of pro?
Probably in that I have a few bespoke induction rules. I guess those use impredicativity, but no, I guess not in an essential way.
And singleton elimination? What do you think?
Singleton elimination, I guess all the time because it's transport, but then I only use it for decidable equalities.
So it should be okay.
Let's just do 2 more questions. Yeah.
Earlier this week, Thomas Hales talked about difficulties he'd encountered where a theorem or concept or structure didn't have a precise definition, and an example he gave was Kelvin phones. And I was wondering to what extent you've encountered these imprecisions, and whether you think that actually significant insight can be gained back to the mathematics community for exposing these.
So I guess the part of group theory I explored was well enough delimited that all the concepts could be narrowed down to precise definitions. However, the notation itself is ambiguous, and there's quite a bit that was gained by understanding by what mechanisms were involved in interpreting the notation, and then figuring out ways of encoding those mechanisms in the so that the Coq elaboration process would do that on its own. And the other bit was things are precisely defined for certain cases, but the definition is sort of a bit too flexible for the odd cases. So I guess the best case in point was what you saw with the quotients. So group theorists have a clever way around this syntactic restriction so as to not have these huge expressions all the time. They resort to a bar notation, what's called the bar convention. So where they will posit, say, okay, suppose h bar equals, say, g over k, and then from there on, a bar will mean not the quotient a over k, because that might not be defined because k might not be a subgroup over a, but just the homomorphic image of a bar under the natural homomorphism from G into, sorry, this should be G, or from G into G bar. And this is playing it really fast and loose because sometimes they'll define a bar to be defined by some equation inside the quotient and then use a. And at which point a isn't quite defined because you might have pieces of the dividing group or not in it, depending on how things are presented. So it's really quite ambiguous. In this case, just having a few more notations, like having this explicit notation for the coset morphism, and also for the inverse image using the coset morphism, which then defines precisely what you want to talk about. That sort of makes it a lot easier to work with.
So it's clear that we could have discussions all day, but I'm going to cut it short. So they'll be over coffee and over lunch. I'm sure George will be happy to discuss this more. So let's thank him once again.
I despaired of getting everyone actually in the same place to talk about social proofs. It's simply on.
Okay.